Good evening, all. Welcome to the week six problem solving session for the course Matlab-Based Programming Lab in Chemical Engineering. Let's wait for like 2 more minutes so that like more students can join, and then we'll start the session. So let's begin today's session. So the problem which we were considering this week was the heat transfer that is happening between a solid body and liquid reservoir. So the question is this: Consider a liquid reservoir at temperature T infinity, in which a body of temperature T0 is immersed at time T equal to 0. The time rate of the change in temperature of the body has a function of time, and the material properties can be obtained by modeling the energy balance of the system. So that is, here you have the reservoir which is having T infinity. T infinity means the for a long, really long time, the reservoir temperature will remain as T infinity. Okay. So now we have a solid body that is T0. It is initially like at T equal to 0. Okay, at exactly T equal to 0, this is immersed in this liquid reservoir. So what happens is, depending on what the temperature of the body is, it could be like the temperature could be greater than the T reservoir, or it could be lesser than the T reservoir. Based on that, what will happen as the time progresses, there will be the temperature will start varying. Either the heat flow will happen from the solid body to the liquid reservoir, or from liquid body to the liquid reservoir to the solid body, depending on whichever is having the highest temperature. Based on the temperature gradient, you will have the heat transfer happening. And what will happen as time progresses, since the liquid reservoir is very huge and its temperature can be kept constant, what happens is the solid body temperature will naturally, it will go to the liquid reservoir temperature. Okay. So the solid body temperature, if it is lower than the liquid reservoir, that is T infinity, the temperature would rise, and asymptotically it will reach to the T reservoir temperature. If it was lower than the T reservoir, so if the solid body temperature was higher than T infinity, then the temperature would drop slowly, and finally it will asymptotically reach the temperature T infinity. Okay. So that's what happens when we have a solid body that is immersed in a liquid reservoir of temperature T infinity. Now we have the governing equation, that is basically the temperature of this body. The capital T refers to the temperature of this body. This changes with respect to time. And how does that changes with respect to time? So the rate of change of temperature is given by this equation. That is dt by dt, where t is time, is equal to minus HAS divided by rho Vc T minus T infinity. So T minus T infinity, that is the difference between the solid body and the liquid temperature. So this is a driving force that will have that driving force for the heat transfer. Okay. So that is T minus T infinity. And what is H? H is a heat transfer coefficient. AS is the surface area of the solid body. And rho is the density of the solid body. V is the volume of the solid body. And C, small letter C, is the specific heat of the solid body. And T is the instantaneous temperature. Why instantaneous temperature? As time progresses, this capital T is changing. But whatever the temperature of T is, the difference between that temperature and the T infinity, that is a liquid reservoir temperature, is what that is causing as a driving force for this entire heat transfer process. I hope that is clear. Okay, now we have the values given for these properties. That is, H is equal to heat transfer coefficient is given as 400 watt per meter square Kelvin. The radius of the solid body is given as 5 centimeter. Density of the solid body is given as 8,500 kilogram per meter cube. And specific heat of the solid body is given as 400 joule per kilogram Kelvin. Okay. And finally, this is the equation that we have. So now what do? We try to solve this. Okay. So we have, like, apart from these properties, we also have two informations that is given to us. That is T reservoir. That is, a reservoir temperature is kept as 25 degrees Celsius. And the initial body temperature, that is at time T equal to 0, the temperature of the body is equal to 100 degrees Celsius. Okay. And now we have to find what, as the time progresses, what will be the temperature of the solid body. So this is an ordinary differential equation initial value problem, or ODE IVP problem. Okay. Why do we say it is like that? We have all these factors, all this HAS, rho, VC, these constants we have. T infinity, which is also a constant, that is 25 degrees Celsius we have. Now we have an equation where dt by dt, that is change in temperature, is equal to T. Okay. So some constant multiplied by T. Okay. So now we know that there is only one independent variable T, and the capital T, temperature, is a dependent variable. So this is an ordinary differential equation. Okay. So we call it partial differential equation if we have, like, two or more independent variables. Okay. So here there is only one independent variable, which is time. So that is why this is a partial differential equation. And why an initial value problem? At time T equal to 0, we know what the temperature is. We know the temperature T, that is equal, given as 100 degrees Celsius. So we know what the initial state of the system is. Now, with that information, we are supposed to know how the system progresses. Okay. At a given time T, what will be the temperature? capital T. That's what we need to find out. Okay. So now this becomes an ordinary differential equation, initial value problem. Now going forward, these are the statements, problem statements that we need to find this time. So that is determine the time required for the temperature of the body to drop to 50 degrees Celsius. Okay. So that is initial temperature is 100 degrees Celsius. From 100 degrees Celsius, it has to drop to 50 degrees Celsius. And what's the time taken for that? Assume all properties to have a constant value as provided before. That is, we assume all these properties. Now, the second sub-question is study the effect of temperature dependence of specific heat and density of the body at the time requirement. So here we know in this equation we have the specific heat that is C and density that is rho. Now we will study that how will the temperature vary if this rho value keeps changing. The next is how will this temperature vary if the C, that is the specific heat value, keeps changing. So we need to study the effect of both temperature and the specific heat. We need to study the influence of temperature, not on temperature, what influence, we need to study the influence of specific heat and density on the temperature. Okay. Now, 45 seconds, we have a new problem statement here. That is 45 seconds after dropping the body into the reservoir temperature ramps up to the following equation. That is T reservoir, that is temperature of the reservoir is nothing but T infinity plus 0.52 T for the next 45 seconds. Plot the evolution of the reservoir and body temperature. So what happens, as I told earlier, the T infinity is a constant value. That's what we took. It is this T infinity reservoir temperature is kept as a constant value, 25 degrees Celsius. But now the system behavior has changed. It is telling that for the first initial 45 seconds, the reservoir temperature will remain at 25 degrees Celsius. Okay, so that is a constant value. But after 45 seconds, the reservoir temperature itself is varying. Okay, how is it varying? The variation is according to this. T reservoir is equal to T infinity, that is 25 degrees Celsius plus 0.5 T. Now you have a reservoir temperature that is a function of the time. Okay. So now then what will happen to the temperature drop? Okay. What will happen to this behavior? What will happen? How will the temperature of the body changes? Now next is developing a phase portrait of the system. We'll understand what this phase portrait of the system is. So, but before that, let me just quickly go to how to solve this problem if we are trying to do this manually. So this is the equation that we have. dt by dt is equal to minus HAS divided by rho Vc multiplied by T minus T infinity. We know that this constant, this every value is a constant. So together we can call this as a new constant, small letter a. So now we have T minus T infinity. Let me call it as x. Okay. Now the equation will be, if I'm taking a derivative of it, okay, dt by d, let me derivate both LHS and RHS with respect to time. So now we know this is a constant. So dt infinity by dt is nothing but 0. Sorry. And this here you have dx by dt, okay, dx by dt, and finally we will have this equation dx by dt is equal to minus ax. Okay, this equation we'll get it from here. Okay, dx by dt is nothing but that is equal to dt by dt, and dt by dt is this equation where we have called this to be a constant a and this to be x. Okay, I hope you get it once again. Okay, so here if you're taking the derivative on both sides, you get, sorry, you get dt by dt is equal to dx by dt, because this tends to, derivative of this tends to 0, not this value, the derivative of it, this tends to 0. Now you can equate this equation to here. Here this is equal to a and this is nothing but x. Okay. So now we will get dx by dt is equal to minus ax. This is a very straightforward equation where you will get e raised to minus x and all when you take the derivative manually. And finally, you resubstitute what this each of the values is. And you also have an initial condition. So when you integrate this, what will happen? You will be getting an integration constant, maybe c or something. And that using the initial condition, if you solve, finally you'll get into this equation. That is temperature at any time t is equal to T infinity, that is the reservoir temperature, plus T0 minus T infinity. This is the initial temperature minus the reservoir temperature multiplied by e raised to minus AT. So now if you look at this portion, you know this is the negative exponential. Okay, so there is an exponential decrease in the value. How will the exponential decrease in value happen? So let us just put t equal to 0. So e raised to 0 is equal to 1. So now finally you will have t infinity, this both will get cancelled. And finally at t equal to 0, you will have the temperature to be equal to T0. So that's what happens. At t equal to 0, the temperature will be T0. Now what happens is the temperature drops. As time progresses, there is an exponential decrease in the value. Exponential decrease in the value, it exponentially decreases. At t equal to infinity, what happens? At t equal to infinity, this is equal to e raised to minus infinity. That is equal to 0. Okay, this term goes to 0. And finally, we'll only have this one. Okay, at finally t equal to infinity, you will have t time, this temperature is equal to t infinity. So this is what happens asymptotically. It never, so in the plot, what happens? It doesn't actually touch this t infinity because that happens in time equal to infinity. Okay. So here we have an exponential drop from t0 is exponentially drops and asymptotically it gets equals to the t infinity at what happens at time t equal to infinity. Okay. That's why this curve goes like this continuously. Any doubts so far? Now moving forward, now we'll also say what is phase portrait. So phase portrait is we'll see for different initial condition how this temperature vary. Okay. So based on that, you will be getting the behavior of the system. So what happens here? The temperature initial conditions. So earlier, what we took is T0 was 100 degrees Celsius, right? T0 was 100 degrees Celsius. So imagine this was for T0 100 degrees Celsius. Now, if T0 is 80 degrees Celsius, I have a different behavior. T0 is equal to 60, I have a different behavior. T0 is equal to 50, I have a different behavior, and so on, I have a different behavior. Okay. And remember, this was 25. That is this T infinity, okay, was 25. Okay. So any temperature above 25, you will have this behavior, this exponential decrease behavior. Now let's see what are the different cases of behavior that is possible. So for example, this is the first case that we said, that is, this is T infinity. Okay, we know that here we have T infinity. So any temperature above T infinity, you will have this exponential degrees as we got earlier. Okay, what will happen if this exponential, this temperatures, right, the initial temperatures that we have is less than T infinity. If it is less than T infinity, this is what happens. Less than T infinity means the temperature of the body, because the reservoir temperature is higher than it, the temperature of the body will slowly start rising. Okay, it will start rising exponentially, but it will tend to go into the asymptotic temperature, that is a T alpha temperature. So if it could be less than, so here what happens is, uh, okay, here what happens is this is the T infinity value. Okay, so it asymptotically increases from the first initial value, it goes on increasing. Okay, this what happens. So here also you'll get a stable solution. At t equal to infinity, it will be equal to T alpha. Sorry, T infinity value. Now this is different condition. This different condition, what happens is here the temperature, we have different initial temperatures, but it is exponentially increasing. That is, instead of e raised to minus alpha minus 80, you have e raised to plus 80. Okay. In this condition, the system will lead to like all the initial conditions, it will go to an it will go to and what you say, a diverging solution, because at time is increasing, the temperature is also increasing infinitely. Okay. So this is not a converge solution. Similarly, in this case, you have a temperature which is less than your T alpha, just like you saw earlier. But what happens here, instead of exponential increase, you have like exponential decrease that is happening. So what will happen as time progresses, the temperature keeps on decreasing and it will have a diverging solution. So this is like a diverging solution. So in this case, the first case one and case two are the called the converged cases that we have. That is, your temperature is greater than T alpha, and there is an exponential decrease in the value. Otherwise, your temperature is less than T alpha and there is an exponential increase in the value. Okay, so these are the only conditions where you will be getting stable temperature conditions. Now, moving forward, so let's see how to solve this ODE. Normally, if you have an ordinary differential equation, how do we solve it? So this is what happens. At t equal to t0, you have an initial, sorry, you have an initial value here. At t equal to t0, you know this value. Whatever is given in star, this value you know. With this information, you compute what is the value at the next point. And with this information, you compute what is the value at next point, and so on. So on, you will be trying to understand how this y value evolves at time equal to t. Okay. So this is what we are trying to solve when we are trying to solve this ODE in MATLAB or any other software. So that is we compare the nearby value of yt using what we already know. Okay, and you keep repeating it until a time that is required for us. Okay, now let me just clear all the drawings. Now, this is what an ODE IVP solver does. So we have an equation. Okay, let it be any equation of the form dy by dt is equal to a function of both y and t. Now we have an initial condition that at t equal to 0, y is equal to y0. Now what we need to find out for whatever temperature, whatever time, okay, whatever time ti, we need to find the y. So here mathematically, this is how you do it. You can write dy by dt like this. That is limit h tends to 0. You can write yi plus 1 minus yi divided by h, provided that h is a very small value. That is what is meant by h tending to 0. Okay. So then dy by dt can be approximated as this, and that is equal to f of t comma y. Now let's just rearrange the statement. Okay. So then it will become yi plus 1 is equal to, take h to the other side and you take yi to this side. Okay. So it will become yi plus 1 is equal to yi plus h of fi. So this is called as Euler's explicit method. There are different methods in MATLAB like Rangakuta methods and all those things. Those methods, if you want to know the basics, you can go and refer to it. But the basic idea is this. So what happens, you assume at t equal to t0. Let's assume I is equal to 0 first. Okay. You know what the y0 value is. You know what is the small step size that is taking, that is user defined. Okay. We take a very, very small step size. And you know what is fi. Fi is nothing but the function value. Okay. T0 is given to you, y0 is given to you. Then you can find out what is f0. That is this. Now the only unknown, so everything you know, yi you know. So here everything you know the yi value, you know the small h which is user defined, you know the fi value because it's only depend on t0 and y0. You know both of them. Now we can find what's the next y. Okay. Now you keep the next y here and then you know what's the small step size. You know what's the time ti plus 1, a time you already know. And fi plus 1 we already found out. You can find out what is fi plus 1. With fi plus 1 you get what is yi plus 2. Okay. Like that, you keep on progressing. So this method is called as Euler's explicit method. I'm just telling you what is the basics math, the max basic behind solving these ordinary IVP equations. But right now what we'll be trying to do is, just a second. Okay. Right now, what we'll be trying to solve is we'll be trying to solve all these equations, the ODE equations using the MATLAB inbuilt ODE solvers such as ODE 45, ODE 23s, ODE 15s. There are several ODE inbuilt solvers that is available in MATLAB. So here we have, this is a general syntax of ODE 45. That is T solve, Y solve. So let me start from here. Okay. ODE 45 is a keyword that you give and you give at the rate a function. Okay. What should the function do? The function should save this part of the equation. That is, if you write dy by dt is equal to some kind of whatever is there in the LHS side, okay, whatever is there in the right hand side, that comes as a function here. Okay, that you write as a function, f name.
जीएससी का क्या
Hello.
था?
Excuse me, Neelam. Neelam, if you don't have any questions, can you please mute yourself? Okay. So first you have an ODE 45 solver, you have a function name, and then what you have to do is you have to say MATLAB from what to what time I should integrate it. I should integrate it. For example, you have a T0 time that is given to you, and I give like till what time I want to know the Y is evolving. So that is called as a range. So you give the range here from T0 to T end, and then you give the initial condition. Remember, you were trying to solve an ODE IVP problem, so you know what the initial value is. That is the t0. What's the y value? That is y0 here. You give that also. Now, finally, what solution do you get? You get a solution. You get some time intervals. Okay, that is from t0 to tn. The MATLAB divides the entire time interval t0 to tn to several time stamps. Okay, and for that time, you will get what is the y value that is there. So that several time is there in this vector t sol, and the y value corresponding to it will be there in this vector y sol. That's what you get. Now, t sol and y sol are the solution vectors. MATLAB will return this y sol for each time t sol. The f name is a function that returns dy is equal to f of ty, f of t comma y. So basically, this part should be there in the function. Now, t0, y0 are the initial conditions representing. That is, y of t0 is nothing but y0. These two conditions, y and t0 should be there. Now, t end. T end is a final value until which the solution is decided. Till what do you want the value, y values to be? So that is a t end. And this is based on RK4 method, which is called as Rangakuta fourth order method. So this is an extension of this Euler's explicit method. You have like different other methods also, Rangakuta, the first, second, third, and all. So this is based on Rangakuta fourth. Now it uses adaptive step size to reduce error. This is like an inbuilt MATLAB thing. So if you understand what is Rangakuta method, you'll understand how this ODE solver works. Okay. Now let us see a basic example of this ODE IVP so that we get familiarized with the syntax and the working of it. So here what I need to solve is y dash. That is dy by dt is nothing but equal to minus 2 ty. And the initial condition is at y equal to 0, it is equal to 1. Okay. And now the analytical expression is this. You can just manually try to solve this and finally you'll get this expression. Y of t is equal to exponential minus t squared. This is what we get. Now let me try to solve this using MATLAB. Just give me a second. I hope I'm sharing MATLAB properly. Okay. Okay. So this is what the function that we have here. We have t0 at time t equal to 0. You have the y0 is equal to 1. So let me just confirm that again. At t equal to 0, y value is 1. Okay, and the function is minus 2ty. So now at t equal to 0, y value is equal to 0, t0 0, and y0 1. And I want to integrate it till what time? I want it to, till tn to be equal to 5. Okay, you can make it 10 or 15 or whatever you want. Right now, I only want it till 5. Now, this is the ODE syntax that we have. That is ODE 45. You write the function. Okay, this is a function that I have. Function, first order ODE, it takes the t and y as variables. And I also tell the ODE solver that here t and y is what I give as variables. Okay, without this also you can work. That is perfectly fine. But here, this part is very essential. You need to call first order ODE t comma y and this at symbol. This is called as anonymous function. This at symbol is also very important. And then you have to enter the range t in the square brackets. Make sure that you enter it in square brackets. It is from t0 to t end. And then comma, you give the initial condition that is y0. Now you get output as t solve and y solve. We will see how this t solve and y solve looks. And if I need to plot it, I can directly plot it. That is plot. In x-axis, I'll have the different time. And y-axis, I'll have the corresponding y values. And I'm keeping the line. It will be a line plot and the line width to be 1.5. Now let me just look what this first ODE fund is. So that is this function. So first ODE fund will take the t and y values and it will calculate this function minus 2ty, which was your function there in the question. Okay. And minus 2ty and it saves in a variable dy. It need not be dy. You can give any variable. Okay. That is completely fine. Here for understanding purpose, I've given minus 2ty is equal to the new variable dy and I give this dy as the output. So this is how you should define an ODE function. Okay. I hope there is no doubt. If there is doubt, please unmute yourself and ask, or else you can put it in the chat box. Now let me just run this ODE. I'm just running it. This is the kind of graph you'll be getting. For time t, you'll be getting the y value changes from y. Initial value was 1, right? So that is why you can see here 1 here. And from 1, there is an exponential decrease and it goes towards this value. Okay, it goes towards 0. Now we'll just see how this y sol and t sol looks. Okay. So you know t sol you started from time t equal to 0 to 5. So that is why the last entry is 5 and the first entry is 0. And you can see by how the different time slots are there, 0.1250, 0.250, 0.3. So you can see the interval between these time intervals are not unique, like it's not a fixed time interval. So that's what I said when I was explaining ODE solvers, ODE 45. It's based on adaptive time steps. Okay, MATLAB itself adjusts the time intervals. So it will not be a uniform time interval. And YSOL will be corresponding to that. So this will be an array of different values corresponding to an array of different values. Both have like 77 values here. This will also have 77 values corresponding to it. Okay. So these both are arrays, and this is how you plot it. You will have the time in the y-axis and the y in the y-axis value. And here you can confirm whether it starts from the right value. At t equal to 0, y value is equal to 1. I hope this is clear. Let me just clear it. Now going back to the slides. Now we have another problem that has been discussed in the recordings. So I'll just quickly show the solution of this. So here what happens? Here you have dy by dx is equal to dy by dx plus 2xy plus x is equal to e raised to minus x square. And the initial condition at x is equal to 0, y value is equal to 1. So now we have to first rearrange this equation so that it is in this form. It is in this form. So dy by dt should be in one side, or rest all the expression should be in the other side. So how do you do it? You have to take it 2xy and x to the other side. So finally it will become e raised to minus x square minus 2xy minus x is equal to dy by dx. And this is the initial value. So manually, if you're trying to solve it, this is an analytical equation. That is y of x is equal to x plus 3 by 2 e raised to minus x square minus 1 by 2. And if you're trying to plot x and y, x on the x-axis and y on the y-axis, you will be getting a behavior like this. Okay. Now we'll try to see the MATLAB code for this. So this was the expression y dash plus 2xy plus x is equal to exponential e raised to minus x square. And y0 is equal to 1. So now the initial condition I'm just giving y0 is 1. And the span, okay, that is the time interval. Here the independent variable is not time, it is x. So the x interval, it is from 0 to 1. And this is my ODE functions equation. That is ODE 45. And I'm telling the variables are x and y. And this is the function that I'm trying to solve. That is ODE FCN. And if the x span I give, it has to be a vector 0, 1. And y0 is like a single value, that is 1. Okay. Now now I'll get the output as in x and y's. Okay. Now what I do, I am trying to create a plot. Hold on. I'm creating a square box. Then I first plot the values that I get from the ODE solver. So x comma y, it has to be 0, say, like the circle markers. Marker size is 8 and the marker its color is black. K stands for black. Okay. Now I need to also plot the analytical function. What this analytical function is, you have already solved it manually, right? So this is the analytical function. I've coded it here. If you give an x value, correspondingly you will get the y value from this analytical function. And xpan I give. So this gives the y value of an analytical function, and xpan gives the x value, that is from 0, 1. And it will be a line with line width 3 and color black. Again, I have x label, y label, and I have the legends also. So basically, now we have two functions here, one for the ODE and other for the analytical function. Let's see that. ODE function will be this, as I said earlier. These two terms has to go to the other side. So it will become e raised to exponential minus x square minus 2xy minus x. This will be dx, dy dx. That will be the output of the function. So this is the ODE function that we need to solve. Next, coming to the analytical function, we have already tried to solve this. So if you give an x value, your y value will be nothing but exponential minus x square multiplied by x plus 1.5 minus 0.5. Okay, this will be an analytical solution. We are trying to plot both together in the same plot. So that is why we have the hold on function here. So let me just try to run this. This is how you'll be getting the surface. So whatever is given in the circles, okay, those are numerical solutions. Okay, and how many numerical solutions you have, we'll just see what is x and y. Okay, you have 41 x's, and corresponding to that, you have like 41 y values. So that's what is being plotted in the circles. And what is this analytical function? You have given an analytical function for a given x value, you will have the analytical function that's calculated. Now we can see how accurate it is. Okay, whatever you get from the ODE solver is exactly equal to what you solve analytically. Okay, the equations are exactly the same. Any doubts?
No.
Yeah. So then we'll be moving forward. What we'll do is now I hope you guys know how to use the basic ODE solvers. Apart from ODE 45, there are some other more ODE solvers are there. I'll just introduce it to you and you can go to MATLAB and check how to use each for your problem. Okay. So the first ODE 45, this is the most popular choice of the solving ODEs and for non-stiff problems. Okay. What is stiff problems? What is non-stiff problems? There are things like that. So that is right now we've only dealt with one variable, like dt by dt, the temperature is the only variable. Okay, so there is only one ODE solver that you are solving. What if you have multiple ODEs to solve? Okay, you have temperature varying with time, you have x values varying with time, you have y values varying with time. If that is the case, if you have like multiple ODEs to solve simultaneously, what happens is your time temperature might be very, very sensitive to time, but your x may not be very sensitive to time, and your y might be too sensitive to time. So what happens is you have multiple variables, and each of these variables have different sensitivity towards your independent variable. Okay, then if your sensitivity is very different, then you call it as a stiff problem. Okay, if all the temp variables like are having same level of sensitivity with respect to the independent variable, then we consider it as a non-stiff problem. Okay, if we have only one equation, stiff and non-stiff, it's both the same thing. Okay, there is no much differentiation between this. So stiff equation means if it has some variables changing much rapidly than others, then it's a stiff equation. Non-stiff equation means if all the variables change at a similar rate, then the solution varies smoothly over a given time period. Okay, in that case, it's a non-stiff equation. So whatever we saw, it's a single equation. So in that, I can directly use ODE 45. It uses adaptive step size, as I said earlier. Now we have ODE 23. ODE 23 works similar to ODE 45, uses a simpler algorithm. So it is RK4. Okay, RK Rangakuta fourth order, that's what ODE 45 uses. Now it is suitable for non-stiff problems again and does not require high accuracy. Okay,
Excuse
so
me,
this is
ma'am.
what. Yes,
Ma'am,
yes.
please explain what is OD 45 or OD 23 like that.
I already showed that earlier. So we have inbuilt MATLAB solvers. Okay, ODE 45 is a function in MATLAB that has been already written in MATLAB. This is what we use for solving ODE solvers. Okay, so
Okay.
far I told you
Okay.
what is the syntax of ODE 45. I'm telling you, apart from ODE 45, there are other ODE, other solvers also available. Okay, and the thing is, you have to choose an ODE solver that is suitable for your problem. So right now we had simple equations. So I directly use 45 because it's the most popularly used one. I can also use ODE 23, but it will have a lesser accuracy. Okay, but it is using a simpler algorithm, which means the computational cost is less. So if you have like a very large problem and you find that okay, ODE 45 takes a lot of time to solve that problem, you can use a ODE 23. Yes, sorry, ODE
Okay.
23. And now next solver is ODE 113. Again, it solves a non-stick problem with high accuracy. It is more accurate than ODE 45. It is uses a variable order, variable step size method. These are the underlying mathematics of this ODE solvers. Now we have ODE 15S. Okay, this whenever you have this S term, this means it is used for solving stiff problems. Like I said earlier, when you have variables which have varied behavior with respect to the independent variable. So in this cases, you can use ODE 15S. It uses a variable order, variable step size method based on backward differentiation formulas. So this is the underlying mathematical equation behind it. So apart from this, there are other ODE solvers also. You can just go and Google it, MATLAB ODE solvers. You'll get a list of ODE solvers and also you'll get to know where and why these ODE solvers are used. Okay, now how to use it is pretty simple. All the solvers has the same syntax. If I want to use ODE 15 years, go back to this equation and instead of ODE 45, just write ODE 15 years. Okay, the syntax remains the same. Just that you have to use the appropriate ODE solvers depending upon the difficulty of your problem. And if you're not sure what solver to use, you can first start with ODE 45 and see how the system behaves. Now, stiff problems can be more difficult to solve numerically because traditional numerical methods may require very small time steps to achieve stable and accurate solution. In contrast, non-stiff problems can often be solved using large numerical time steps with good accuracy. So basically what I'm trying to say is stiff equations are difficult to solve So if you are using ODE 45 for stiff equation, you might not get accurate solutions. Okay. So if you know your system is stiff, directly go for stiff solvers. Otherwise, go with the normal non-stiff solvers like ODE 45, ODE 23. Now coming back to our problem statement, we'll try to solve each and every part of it. So actually in the recorded lectures, you have only the code, complete code is only given for the first part, and the sub question 2, 3, and 4 sub parts, the complete code has not been given. It is up to like you are supposed to, like sir has explained to you how to find the solution. So I'll just show you quickly the codes for all the 4 parts. Okay, so that you can compare your codes with it. Now coming to the first part, determine the time required for the temperature of the body to drop to 50 degrees Celsius. Assume all properties to have constant value as provided before. Now let's go to this part we've already know. Okay, I mean this we know how to solve this ODE. If you have an ODE like this right now, we know how to solve it. Okay, so we get the time temperature as a function of time. You can get that behavior. You can plot also, just like we plotted in the previous 2 examples. You can plot now. Okay, now before that, let me just show this part in the code. So this is the first part of the code. First, what you have is this is a function. Okay, the ODE solver function, right? So that is I'm giving the function name as reservoir. Now the T final is 50, 500. So T final is 500. In this, if you check the units, we had some constants given to us, right? So in that constants, in the constants we know here everything is given in okay watts means it will be by per second, right? So time will be in seconds, and also remember that your temperature is in Kelvin, which means this degree Celsius has to be converted into Kelvin. Okay, before we start the calculations. So now your T final, that is your time final is 500, final time is in seconds. Now T span goes from 0 to T final, 0 to 500 seconds. Now T initial, initially it was given as 100 degrees Celsius. Okay, if my initial temperature of the body is 100 degrees Celsius, convert into Kelvin. So that will be 100 plus 273 Kelvin. That is your T initial. Now you have your ODE equation. You are telling ODE, calling ODE 45. You're telling this is the fun. Fun is this. Okay, remember you have this anonymous that's at the rate simple and the reservoir. Okay, that goes here. You have the T span, which is a vector that is having 0, comma T final. And this is their initial value. Initial value is 373 Kelvin. Okay, basically 100 degrees Celsius, you have to convert into Kelvin and Kelvin. Okay. Now you will get an ODE solver. What the answer you will be getting? You will be getting corresponding time. Time will be varying from 0 to 500 seconds. Depending on that, you will have the Y value. Okay. Now my target question is, we need to find out, okay, for time being, I can just plot also. Plot T comma Y uh, line with the 2. Okay. Now let me just run this part of the code, and then we'll go into the deeper one. So you'll be getting like this exponential degrees. It started from 373, that is 100 degrees Celsius. It goes exponential degrees, just like we observed in our slides. Now coming back, we need to know one thing. What is the time when the temperature becomes 50 degrees Celsius? So initially it was 100 degrees Celsius. From 100 degrees Celsius, you have to go to 50 degrees Celsius. What is the time required for that? Okay. So now if you directly look at this T and Y, you know this T value, it is not uniform intervals. Okay, the intervals will not be uniform because you're using ODE 45, it has an adaptive time step. And depending on that, you have our Y values. Okay, so in Y values also, you'll not be able to plot exactly where the 50 degrees Celsius is. That is 50 plus 273. Okay, you'll not be exactly able to point out where 50 degree is. So, and also there is only how many grid points are there? There is only 41 data points. So what will happen is you might have a temperature that is near to 50, but not exactly 50. So now what do you do it? If you what the first thing you can do it is this 41 points, right? Between these 41 points, let's generate some more points. Let's just interpolate and create some more points. So for that, you have an inbuilt MATLAB function for interpolation and generating more points that is called as interrupt one. So what input what you have to give? you have to give the whatever existing data you have. That is 41 time. And according to that, 41 y values you have. So that you give. And along with that, you give the final grid of time. So final grid of time is from 0 to t final. That is from 0 to 500. I'm generating at within time interval of 1. I'm generating t fine. Okay, so this will have 500 points. So that is my 500 points time. And I'm telling interpolate it by spline interpolation. There are different kinds of interpolation method, and spline interpolation is a very, very widely used one. If you want to know the max of it, you can just go Google it and see. So that is, we are trying to interpolate using spline interpolation. Okay, now what will happen is I'll just run the statement. I'll just evaluate this for you. Okay, now if you look at this part, the actual y was only 41 values. Now, but y fine has 501 values. Okay, now we have like a very fine grid. Now what you have to do is you have to find where 50 is. So for that, easiest way is you can find what is the difference between each y fine value is there, no? Okay, subtract 50 degrees Celsius. Remember that value is given in Kelvin. So y fine minus 50 plus 273. Okay, you have to convert into Kelvin and then subtract. So what will happen? You will get the error function. So error function, what will happen is you will see how the error function behaves. The error was 50. It keeps on decreasing. Okay, it keeps on decreasing 40, 35, and finally at one point you will see that it will be equal to 0. Let me just see where is that 0. Okay, it is very 7, 8, start increasing. It's very difficult also numerically, like visually finding it. What will happen is at one point the error value will be 0. That is where the pi fine was almost equal to 50 plus 273. So now what will happen? We'll just concatenate. This catenate means concatenate. So I'll just tell you help cat. Okay, this is what happens in help cat. What happens is this is a syntax. You give the dimension, you give a comma b. It basically concatenates the array a and b along the dimension dm. So if you give cat 2 means you will be getting columns basically. Okay, a and b as columns. If you give cat 1 comma b, you will be getting different rows. A is one row and b will be the next row. So that's exactly what I'm doing here. Cat, I'm telling it should be different rows, and first value will be t fine and corresponding y fines and corresponding error values. So I'll just run this again. So I'll just show you what this ARR looks like. ARR has T values, corresponding temperature values, and corresponding error values. And now what do? I need to find where the minimum error is, because at the minimum error, it will be very, very close to 50 degrees Celsius. So I take minimum of third row. What was third row? Third row was the error values. Okay, minimum of that. Okay. And corresponding to the minimum, I find ARR that is corresponding to minimum. I find what is a row and column for that. For this minimum ERR, what is the row and column number? Now from that, I'll be getting that row and column number will give me where the temperature and the corresponding time is. The time required for the temperature to reach 50 is nothing but ARR 1 comma column. So the one gives you the first row of ARR gives you the time, right? First row gives you the time, and which column you have to take? The column that is corresponding to the minimum value. So the column you get it from here. And what is the temperature corresponding to that? Sorry, what is the error? Error or the uncertainty corresponding to that? For that, you have to take ARR. Third row is what? Third row is the error basically. And the column corresponds to the minimum one. Now, when you run this whole thing, let me just clear it. CLC. You'll be getting this curve and you'll be getting time required to reach the temperature to 50 is 156 seconds. Okay, and you can't exactly reach 50. So based on there is like a small difference. Basically, the temperature you're getting using your final grade is 50.063977. Okay, if you want much more less uncertainty, what you have to do is instead of 500 points, you had interpolated to create 500 points, you can create like 1000 points, 1500 points or something. You can make it even finer grid. So you'll be getting less uncertainty. Is this part clear? Any doubts? Now let's go to the next question, next sub question. So the next sub question is study the effect of temperature dependence on specific heat and like we have to study the effect of temperature on specific heat and density of the body on the time requirement. Okay, basically what happens is there are several ways to do this. I'll just show you the simplest way. What will happen is you will change for the specific heat values. You will try to solve the ODE solver, and then you will get a graph. Okay, just like this, you will be getting you'll be getting a graph like this for a specific heat. And now what you do, you again change the specific heat value to a different value, you'll be getting a different curve. So basically, you'll be getting several curves as you change the specific heat capacity. And similarly, for density also, you can do the same thing. For a single density value, solve the ODE, and you change the density value, solve another ODE. And similarly, plot all this curve together in a single plot. So that's what I'll be doing. Just a second. Let me just show MATLAB. Let me just clear all this. So if you're looking at this constant specific heat, this is what we get. For constant specific heat, everything remains the same. T final is 500 seconds. T span is from 0 to 500. Initial temperature is 100 degrees Celsius converted into Kelvin. So that is 373 Kelvin. And what I do is initially my C value was a single value, right? So my C value was what? I'll just look at, okay, I just forgot to show you the reservoir. Okay, reservoir command will be like this. It will have all the constants given. H, rho, A, R, everything will be given. And this will be the final equation. Okay, this constant multiplied by T minus T1, where T and small letter t, that is both time and temperature is the variable here, and dF will be the output. So here, what happened is we had the specific heat to be 400. Now, instead of taking 400, let me take different values, 300, 400, 500, 600. Okay. Now, what happens is I run a for loop so that I can go for each, I can calculate for each C value. So the for loop goes from 1 to length of C values. And the first time it takes the first value. Okay, C is equal to C values 5. So first it takes 300. Then I calculate this function. This is my, instead of earlier I had the reservoir function. Now instead of that I have reservoir temp depth function, which takes three inputs. It takes time, temperature, and C also as input. I'll just show you this function. Okay, it takes three inputs, T, time, temperature, and C. So based on that, what happens? The temperature, you get it from here. It will be user-defined temperature. It is not defined here among the constants. Now, going back, you get that as a function. Now you can solve the ODE for that. So that is T comma Y given in square brackets. You have ODE 45. You call this function. Function is basically this. Remember, you have to put this at the rate simple. And T span, and you have T initial, that is nothing but 373 Kelvin. Okay, now we plot it. Now the plot, what happens is I am plotting time and I am plotting it in degrees Celsius. Okay, so that is why it is y minus 273. Then I plot it for different C's. So first plot is there. Okay, and again I have this hold on function, right? So again the second plot for C equal to 400, again the plot will be on the same figure. For T equal to 500, again you solve it, and T equal to 600, you again you solve it. And similarly, this will be the final graph you're getting. This will be the behavior you'll be getting. Okay, if you're analyzing it qualitatively, you'll see that for C, this is for C equal to 600, this is C equal to 500, this is C equal to 400, and this is equal to C equal to 300. So this is decreasing values of C. Okay, when C values decreases, you can see how the slope changes. Okay, when the first one is for C equal to 600, the slope is like all flatter, but for C equal to 300, the drop is very quicker. So that is a temperature drop when your specific heat capacity is less, okay, is higher. So the temperature drop is higher when C equal to 300 compared to C equal to 600. Okay, and you can see all this three goes towards the asymptotically, it goes to 25 degrees Celsius, which is your reservoir temperature. Everything goes asymptotically towards 25 degrees Celsius itself, but the rate at which it drops is different. So this is in the decreasing order, decreasing this. If you go from this direction, it is in the decreasing order of C value. That's a specific heat. Okay, let me just compare this with the solution that we get. Okay, for decreasing value of C, this is the behavior you get. This is in the decreasing order of C. Similarly, you can vary it for densities also. So for densities, what I do is the same code itself, but see, everything remains the same. Earlier, the density that I took was rho was 8,500. Now let me vary the rho. Okay. So now rho I am telling it can take values 6,000, 7,000, 8,500, and 10,000. Okay. And instead of earlier, it was going through each of the C values. Now I have a for loop that goes through each of the row values. So now row is takes 6,000 first. Okay. That takes the row initially takes 6,000. And again, this is my new function, reservoir row. I'll just show you the function. Okay, it takes time, temperature, and rho as an input. It is not defined here in this. Rho is a user-defined value, and you calculate df. Now that is your ODE equation. Now this will be the ODE definition here. ODE 45, you call this function. T span remains the same, T in remains the same, exactly what we did earlier. And you plot it, you are plotting y in degrees Celsius. So that is why you have minus 273. And you have this hold on. So basically what happens, every plot in the for loop gets plotted on the same figure. And finally, I'll just run this and show to you. Okay, finally, this will be the plot. So what happens when rho is equal to 10,000? This is the first, the violet one is rho is equal to 10,000, rho is equal to 8,500, rho is equal to 7,000, rho is equal to 6,000. So this, if you go from this direction, this is the decreasing order of rho, decreasing order of density. Okay. So higher is the density, lower is the temperature drop. Okay. The temperature drop is pretty slower, but lower is your density, the temperature drop is pretty high. That is why the slope you see, it is pretty steep. And all this condition, it again asymptotically goes to the T reservoir temperature, which is 25 degrees Celsius. Is this clear? Any doubts? So if not, let us go to the next part of the question. So again, I'm just comparing. So decreasing value, this is the order of decreasing value of the densities. Now, next question is, we have to go back. So next question is, up to 45 degrees, up to 45 seconds, the T reservoir temperature is a constant. And after 45 seconds, the T reservoir temperature keeps changing. Okay, as T infinity plus 0.5 T, it increases with respect to time for the next 45 seconds. So now we need to understand how the temperature drop is for both T reservoir and T, that solid body. Okay. So this is a solution that you get generally. From the recorded lectures, you have this plot. So T reservoir, in initial 45 seconds, it will be 25 degrees Celsius itself. As time increases from 45 degrees Celsius, your T reservoir temperature increases. It's a straight line equation, basically. So you get an equation like this. On the other hand, your Y sphere, it will drop. Okay, till 45, it will be the behavior that you expect in your actual one. But after that, there is a decrease in, there is a change in slope. Okay, that we'll observe. So let me just show you the code first. Okay, first this part of the code has been given in the recorded lectures. We have the reservoir. There is a new function that is there. I'll show you this. T final is 90 seconds. So basically, you have 45 seconds plus 45 seconds. So the total time interval you decide is only 90 seconds. So your T span is from 0 to 90 seconds. T initial is 373 Kelvin itself. And now you have the ODE fund that you solve. Okay, now how does this T reservoir changes? So the T reservoir, what happens is we have a for loop that is there. Fine, first we are telling all to be T reservoir temperature. It will have the same length as a time. Okay, so there are 90 time. There will be 0 to 90. Similarly, you have 0 to 90. T reservoir temperature, first let us declare all values to be 0. Now you're telling that if the time interval is less than 45, now the T reservoir temperature will be 25 plus 273. Okay, whatever the value is, 25 plus 273. It is not dependent on your time. Now, when the time is greater than 45, what happens? Your T reservoir temperature is 25 plus 0.52 multiplied by Ta minus 45. So plus 273. This is for converting it into Kelvin. So this is how the straight line equation, basically whatever we had, we are writing it for T is greater than 45. So this will be the T reservoir behavior. And you can plot this. So basically you can plot T reservoir in the y-axis and this T span in the x-axis. You will be getting how the T reservoir temperature varies. Now the tricky part is you need to know how the reservoir 2, How does the ODE solver solve this? So in the ODE solver, let us go to this function, reservoir 2 function. Okay, this is a reservoir 2 function. All the constants remains the same. The only thing is you put this equation here. That is, if T is less than or equal to 45, T reservoir is nothing but T infinity, which was 25 degrees Celsius, or converting into Kelvin. And when T is greater than 45, basically remember T was an input that is given. Okay. When T is greater than 45, you have this equation, T infinity plus 0.5 T minus 45, this equation. Now this T reservoir comes here. Okay, now what happens? Based on your small t, based on your time, T reservoir temperature can take either this value or this value, and that will be placed in your ODE equation. So this is how you understand this. Okay. Now that basically solves the ODE 45 equation based on that equation. And now I'm plotting time versus the ODE solvers, basically the solid body's temperature in degrees Celsius. And on the same plot, I'll be plotting time versus reservoir temperature in degrees Celsius. So let me just clear CLC. If I run this, this is the behavior you'll be getting. Same as we observed, T reservoir temperature. It will be a constant 25 degrees Celsius till 45, time 45, and from that it will increase. It's a straight line equation. You have the temperature dropping. So to understand how this functions different from um, the initial drop, let me just plot that also. Just a second. Just a second. Mm, Yeah, this was the first function, right? I'll just run this also. Let us see how this curve. No, just a second. Oh, it has to be plotted in degrees Celsius. So just a second, I'll just write minus 273. Okay, clear, close all. The first one is reservoir. Just a second. Okay, this was our first code. Let us run this. We got this curve. Now hold on. I have this first function, which I already have. I'll just run this command again. Now let us look at this curve. Okay, see here the variation is there. I need not plot up to 500 degree. We could only plot up to like 45. So basically you see a difference in slope here. Okay. Let me just zoom it for you. See, there is a difference in slope. Up to 45 with the exactly the same, whatever behavior that we observed, that behavior is there. But after 45, you will see the temperature drop. The curve, the rate at which the temperature drops has varied because your T reservoir temperature is varied. So this yellow one was the initial system that we observed. Now the T reservoir is changing. You have this blue curve. I hope that is clear. If you have any doubts, please do unmute yourself and ask. Now coming to the phase portrait, right now we have varied the specific heat, we have varied the row. Now I think it will be easy for you to vary the initial values. So if you vary the initial values, you'll be getting different plots. Okay, so let's create the phase portrait. For that, let me just close all. Just a second. Close all. CLC, clear CLC. Let me just close all these functions. There's a lot of functions. Yeah. Now you need yeah. This is for the phase. So phase, what happens? The only thing you have to vary is your T initial condition. So the T initial condition earlier it was 373, right? 100 plus 273, it was 373. Now I'm taking temperatures less than 373 and also greater than 373. Let's see how the graph looks. Okay. So I'm taking 73 Kelvin, 100 Kelvin till 473 Kelvin I'm taking. Now what happens? The same for loop you have, but this time the for loop has to loop with the initial values of temperature. So I have I to length of T initial all, and T takes the first value. First it takes 73, then in the loop it takes 100 and so on. I have the reservoir function, the same reservoir function that we had. Now ODE solver solves it and we are plotting it time versus in temperature in degrees Celsius. Okay. Now let me just run this code. So this is how you get. Okay. So remember for 100 degrees Celsius, this graph, okay, from T equal to 100, this we have already observed. When the temperature is above 100 degrees Celsius also, there is an exponential decrease and it goes asymptotically to temperature is equal to 25. But when the temperature is below 100 degrees Celsius or the temperature is like less than 25 degrees Celsius, you will see the temperatures exponentially increases and asymptotically it goes to 25 degrees Celsius. So this is a combination of two graphs that we saw earlier. Okay, we had seen like two graphs. So this is a combination of case 1 and case 2. If you are able to place case 1 and case 2 together in a plot, that is what we get. Okay, when your initial temperature is less than your T alpha, this plots you get. When your temperature is greater than T infinity, okay, then the top plots you get. But all asymptotically goes to your T infinity, which is 25 degrees Celsius. Is this clear? So if this clear, let me just show you the some questions. Okay, I'll give you few time to like few minutes to try to solve it. So once you have the answers, like put it in the chat box and then we'll discuss it. Okay. We have like around 15 questions. So take your time and we have like almost like an hour. Okay, and we have numericals also and we have multiple choice questions also. So I'll give you 2 minutes for each question and please put the answer in the chat box. Okay, and try to answer this because these questions are very similar to what you get in your assignments. So it will be helping you to solve your assignments and even your final exam. So yeah, take your time and let me know your answer in the chat box. So what is the question we have? So for cooling a solid body in a reservoir in phase portrait temperature versus time. Okay. So basically the last plot what we have, the temporal evolution is a function of what? Specific heat only, density only, both specific heat and densities and does not depend on the specific heat and density. Okay, this behavior we have already seen. We know that the phase portrait, basically the temperature evolution of that solid body depends on both the specific heat and density. So that is why when we are So the answer is both specific heat and density. That is why when we vary the specific heat, you get different plots, and when you vary the density, also you get the different plots. Okay, so both the temporal evolution is both a function of specific heat and density, right? Now going to the second question. So just think for a bit and sorry, this is 100 degrees Celsius and 40 degrees Celsius. Okay, think for a bit and tell me the answer. Okay, hope you remember how the like the constant. This is what different density, right? For different density, we had plotted this and just take some time and think and let me know the answer. Any answers for this? So this is how for cooling of a solid body in a reservoir, if temperature drops from 100 degrees to 40 degrees, okay, what will be the order of the time required for different densities? So now the different density is rho 1 is greater than rho 2, greater than rho 3, greater than rho 4. So basically, this is decreasing value of rho, right? So here, you will have rho 4 here and rho 1 here. So rho 1 is here and rho 4 is here. Now, what happens the time? So we have said that for a for a lower density, the temperature drop will be higher. Okay, that is the time required will be lesser. Okay, so that is for a so basically your row and time. So the what I said is for a lower density, temperature drop is higher. So time required is lesser. So that is time also is lower. So basically you will have the same behavior as densities. If rho 1 is greater than rho 2 is greater than rho 3 is greater than rho 4, then T1 is greater than T2 is greater than T3 is greater than T4. You'll have the same behavior. Okay. You can just think for a bit and if you have questions, you can ask me. Again, this is decreasing value of density. Lower is your density, faster is your temperature drop. That means lower will be the time taken. Okay, it's directly proportional. Now again, you have another question that is related to tank flow. If you have an ODE equation, dH by dt, here h height of the liquid height is the liquid height is your dependent variable. It is dependent on time. And you have Qi minus Q0 by A. You have all these values that is given to you. You have to find, you have to use ODE 45. Find height of the liquid at 10, 20, 40, 60 minutes. Okay. I'll give you like 2, 3 minutes. Just think about it. And if you have MATLAB, please try to code it, or else you can just take a pen and paper and try to code the ODE function and the ODE 45, that equation, right? Also try to write that and we'll discuss the answer. Anybody with answers? So here you have the other A is given, A value is given, Qi is given, and you have your uh, okay, you have G equal to 9.8 and Q0 is given as a function. So it is A square root of 2GS, but small letter A is given as 0.008, G value you know, H is a dependent variable. So Q0 is a function of H, okay? And then you have an initial value that is a T equal to 0, your height is 0.1. And you have to find you have specific time that is given to you, 10, 20, 40, 60. So let's try to solve that in MATLAB. I'll just close this first. So this is how you write at time t equal to 0 or your height is nothing but 0.1. And instead of giving, okay, this is a trick that you can use. You have an initial temperature, initial time that is 0, okay? Instead of t span, right? Instead of t span, you only give two values, basically the first value and last value. Specifically, if you want a particular time, okay? To know if you want to have a particular independent variable at specific intervals, if you need to find the value, you can give that intervals in this vector. So basically your t in this 10, 20, 40, 60 and your vector that you give is t0 to tn. So basically this will have 0, 10, 20, 40, 60. So like that you can give your t span. And h0 is your initial condition, t equal to 0, h0 is equal to 0.1. And this is your ODE equation. So let's look at the ODE equation, that is a prop 3 fun. Just a second. You have your ODE equation. What does it do? It takes the t and h, that is t and the height as a variables. All the unknowns, the known quantities are given here. You know, Q0 is a function of h. So Q0 is a square root of 2gh. So based on the h value, you calculate your Q0 value. And your dh dt is nothing but Q1 minus Q0 divided by a. Okay, so that will be what the output of this function will be. So I'll just run this section by section. Let me just clear. Okay, so the first section is you get Tn equal to 10, 20, 40, 60. And again, I'm running this. So what will be this? I'll just run the section for you. Okay, so here the time, here time span is 0, 10, 20, 40, 60. So again, I'll just run the section. See, so what happens is your T-sol, I'll show you what will happen to is. T-sol will just exactly take the intervals that you desired, whatever you gave in T-span. So if in T-span, if you give just one value, that's the upper limit and lower limit, the T-span, the time intervals will be decided by ODE 45 by itself. Okay, it will tell you, it will automatically calculate which time intervals gives you the most stable answer. It will give you time intervals accordingly. But instead of T-span, instead of if you're giving two values, if you give like different intervals, exactly at that point, it will give you the what is the y value. So you have your 0, 10, 20, 40 as your t zone, and your corresponding heights will be 0.1, 0.2831, 0.3744, and so on. Okay. Now let me just plot this t sol and y sol, and we'll plot this together and run the section. This is the figure you'll be getting. For time, this is how the height varies. Why it is, you can see it's a straight line from here to here, here to here. It's like, it's not a smooth curve. Why? Because your T-span, you have given specific values. It is not, it doesn't have like 40 points or something. If you have, if you're giving, if you want smoother curve, just give the lower limit and upper limit, and the MATLAB itself will give you a very, very smooth curve. Otherwise, if you, right now the question was to find the t values a specific time. So that is why you get straight lines. This is like sharp, sharp curves. Okay. And this is your t sol and corresponding h sols. Is this clear? Any doubts? Okay, so if you're given a specific time and if you want to find the specific y value corresponding to it, you can do it this way. But if you're giving a specific y value and to find the specific t value corresponding to it, which is a little bit tricky. That is what we did in the first part of the question. In the recorded lectures, whatever we discussed, the reservoir problem, the first sub-question what we did does the opposite. That is your temperature is given to you and you need to find the corresponding time. This is the opposite. The time is given to you and you have to find the corresponding temperature. Sorry, here it is the height, corresponding height. Now going to the next question. Again, a similar question for different specific heat, how does the temperature varies? I'll give you 2 minutes. Please put the answer in the chat box. What are the answers? So here the behavior is for a cooling of a solid body in a reservoir, temperature drops from 170 degrees Celsius to 30 degrees Celsius. Okay. What will be the order of time requirement for specific heat? So similarly, what we said earlier is lower is the specific heat, higher will be the temperature drop. So lower will be the time required. So basically, the specific heat and time is also directly proportional. So if C1 is greater than C2 is greater than C3 is greater than C4, then T1 will be greater than T2 will be greater than T3 will be and T4. The same behavior we'll have. Okay. Any doubts in this? Now we have a different ODE equation, that is exponential population growth is given by dP by dt. Just read this question once. You have P and R given to you. K is the carrying capacity. Initial population, that is T is equal to 1, population is equal to 10. Find the population at the end of 100 years using ODE 45. Your R and K value is being given to you. Just write the two equations, basically the function and the ODE line, ODE function line, and then we'll discuss the answer. Any answers for this? So we'll look at the code. So T span is from T equal to 1 at time, that is at year 1 from year 100. So 1 and 100. P0 is that is the initial population. At year 1, the population is 10. So now we have the ODE 45. You call this function that is pop ODE fund. T span is given as 1 to 100 and P0 is nothing but 10. Now we'll just see what is ODE population ODE 45 fund is. So it has a constant R is equal to 0.65, which was given to you in the question. K is equal to 38. That is also given to you in the question. Now the equation is dp dt equation is Rp multiplied by 1 minus P by K, where P is the input that is being given. Okay. Now that will be the ODE solver equation. We'll try to solve this. Now we can plot time versus population. Now let me just plot it for you. So basically what happened is in the first year at year equal to 1, the population was 10. And then you have an exponential increase in population. And finally, at t equal to 100, the population is 37.83. So that is the answer that we want. Okay. Or otherwise, you can just go see what is the pop. And finally, final value will be corresponding to t equal to 100. That is 37.8. So the answer to this question is 37.83 will be your population. Then this is how the population increases from 10 to 37.3 as time goes from 0 to 100 years. Is this question clear? I'm sure that by now you know how to solve ODE solvers. Like just let me know if you have any doubts. Moving on to the next question. It's a very quick question. I'll give you 1 minute. Please put the answer in the chat. So for cooling of a solid body in a reservoir, having constant reservoir temperature, basically the question that we try to solve, temporal in evolution with different initial temperatures, having initial value makes the system unstable. Does it? No. So we have seen that that is negative temperatures means when your temperature is less than your reservoir temperature. Okay. So then we saw that the system is stable because all temporal evolutions go to an asymptotic limit, right? We even tried solving the last part when we were looking at the phase portrait. We saw like when the temperature is less than your T infinity, you have asymptotically the curves are increasing and it finally reaches your constant temperature, reservoir temperature. So the answer is no, it is not unstable. Now the next question, I'll give you 1 or 2 minutes. What is the answer for this question? So if the reservoir temperature is constant, then temporal profile of the body must be between the initial temperature of the body and the reservoir temperature, option C, that we have already seen the plot. So first it starts from the initial temperature and asymptotically it goes towards the reservoir temperature. So it has to be between the initial temperature of the body and the reservoir temperature. I hope that is clear. Now the question number 8. For cooling of a solid body in a reservoir having constant reservoir temperature, the temporal profile of the body is. It's a very quick question. I'll give you 1 minute. The answer is the cooling of a solid body in a reservoir having constant reservoir temperature, the temporal profile is an exponential function. It's an exponential decreasing function. It starts from the initial temperature of the body and it exponentially increases or decreases, whatever, depending on how the temperature is. And then exponentially goes to what? It goes to the reservoir constant temperature. Okay. Now we have a next question. Just okay, this is what I said. You have like three variables, dependent variables. We have S, X, and P, all three depending upon time. Okay, so this is a system of ODE equations. You can just think about how to solve this, and then I'll tell the answer. So here we have three equations and we have given r as a value here and r is a function of sx and so it is 25xx divided by 15 plus s. So other parameters are given to you. D is equal to 4, S in is equal to 5, and Yx is equal to 0.7 and Yp is equal to 0.3. Now we have the initial condition that is a t equal to 0. Okay, we have the S, X, and P. In this order, you have 5.0, 0.1, and 0. Now we need to use ODE 15S to solve the following systems, and we need to obtain the concentration at t equal to 1 and t equal to 10. Okay, now we have different sub-question. What is the product concentration at T equal to 1? What is the sugar concentration as T equal to 10? What is the biomass concentration at T equal to 10? And what is the product concentration as T equal to 8? Basically, at T equal to 0, sorry, T equal to 1 and T equal to 10, we need to get X, X, and P. S is sugar, X is the biomass, and P is the pharmaceutical product. Is this clear to you? Now let us go to the MATLAB equations. Here, CNC. Let me just close this. Okay. So first, what I am doing is I have some parameters. This I have declared it as structures. Like it's not very. You don't have to save it as structures. You can just write SIN is equal to 5, D is equal to 4, YCX is equal to 0.7, YCP is equal to 0.3. Basically, I declared all the constants. Then I have the initial condition. Remember, earlier in initial conditions, you just had one single value. But here it will not be like that. You will have a series of values. So corresponding to S, X, and P. So you have to give it as a column vector. Remember that. So it has to be 5.0, 0.1, and 0 as a column vector. This is your initial value. Your initial time is 0. Your T end, you have to do it from 1 to 10. And your T span will be, remember this, your T span will be 0, then 1, and remember 10. Why do we do this? You have, earlier we have said, right, if you want specifically at some time when you want to calculate, you can directly give that value, the time intervals in the T-span itself. So your 0 is initial time and T end is 110. So your T-span will be 0, 1, 10, right? And then you give to the ODE solver, ODE 15 years. This is a function that we have, reactor fund. It takes in T, Y, and all these parameters. Okay. Right. That is why I just want to save it in a single param. It is a structure that we use. That is why I saved it like this. In case you are not comfortable with structures, you can give in a bracket, you can give SIN, DN, YCX, and YCP. Or else directly in the reactor fund itself, you can declare all these variables like we used to do before. Now T-span is there. You have 0, 1, 10, and Y0 is the initial value, this column vector. Okay. Now going to the reactor fund, we have all the parameters here. We have the param, the structure has been passed. From the structure, you take all the parameters, or else you can directly declare here itself. SIN is equal to D equal to directly you can declare here. And from the Y is a vector, right? So Y, you know, here there are three values. That is, Y is a vector. The first value of Y is X, second value of Y is X, and the third value of Y is P. So that you have to take it out. So that the first value of Y is S, second value of Y is X, and third value of Y is P. You write what the R is. R is a function of both X and X. Now we have to write three equations. Okay, the ODE equations. But the thing is, this ODE equations earlier you just had one output, right? Here also you'll have only one output. But the thing is, you will have it as a column output. First row will be the first equation, second row will be the second equation, and third row will be the third equation. Okay, so this is first row. So everything is a single column. So 1, 1, 1 means it's a single column. But this is first row, you will have the first equation. Second row, you'll have the second equation. Third row, you'll have the third equation. So this is the syntax you have to use when you have multiple ODEs. The output functions, right? The output ODE function should give you each of the ODEs as different rows in a single column. And the initial value that you give should also be a column vector. So the function has to be a column vector, the initial value has to be a column vector. So that's what you do. Okay, and fval will be the output. I can run this and show to you. Clear. PLC. I'm running this. Just a second. Prop 9, line 19 is incomplete. So I get to have a, yeah. running this. Yeah. Now, how do we extract the values? So this is here. What is output? TS and YS, right? So TS is here, YS is here. Okay. At t equal to 0, corresponding to that, your S value was 5, X value was 0.1, and P value was 0. T equal to 1, corresponding, S value is this, X value is this, P value is this. And corresponding to t equal to 10, X value is this, S value is this, sorry, X value is this, and P value is this. So you have the YS given here. So if you know how the YS looks, you can simply extract it using the YS index. Okay. At t equal to 1, product concentration means t equal to 1 is what? T equal to 1 is the this one, right? So the second row, third column. T equal to 10 means it will be the third row. Sugar concentration will be the first column, so 3, 1. Biomass concentration will be the second column, 3, 2. And the product concentration will be 3, 3 for corresponding to time t equal to 10. So that's what you extract from here. If you know the how the YS looks like, you'll be able to extract it appropriately. And finally, you'll have the values here. Is this clear? Any doubts? I hope it is clear. Now moving on to the next question. Just give me a second. So this is the next question. I'll give you 1 or 2 minutes. So in the phase portrait of temperature versus time for cooling of a solid body in a reservoir at a constant temperature, basically the phase portrait that we saw earlier, what does it imply if the curve becomes nearly horizontal as time progresses? The answer is simple. It is answer B. That is the body has reached the thermal equilibrium with the reservoir. Okay, that is the body temperature has been equal to the reservoir temperature. That is what we mean by thermal equilibrium with the reservoir. I hope this is clear. Moving on to the next question. If a solid body is initially at temperature T0 and cools to temperature T1 in time T, how will it will cool to T1 to T2 if T2 is closer to the reservoir temperature? Okay, just think about So how will it behave? Like when you have a temperature going from T0 to T1, and then you have T1 to T2. Okay, so if you remember, if T2 is closer to the reservoir temperature, that is as we get closer to the reservoir temperature, if you look at the curve is almost flat. Flat means the rate of change of temperature is very small. When the rate of change of temperature is very small, what happens? The time taken for cooling, it is larger. The time is larger. That is, more time is taken for the temperature drop. That is what you mean by the rate of change in temperature is low. So the temperature difference between the solid body and the reservoir decreases. The rate of cooling decreases as well. That is why the slope, basically the slope is almost flat, which means the rate of cooling decreases. So the cooling from T1 to T2 will take more time. Okay, because the cooling is right now very slow. Because of that, the time taken will be longer than what was exact earlier observed. So the answer is B. Any doubt in this? Now moving on to the next question. Again, you have, okay, earlier I think I didn't mention this. You have to use ODE 15 years. Okay. So if you look at the syntax for ODE 15 years, see, everything remains the same. Okay. The syntax remains the same. Instead of ODE 45, you just write ODE 15 years. Rest everything remains the same. Okay. So we have one more question here. Y dash is equal to Y2, Y3, and you have like three equations, three initial conditions. You have to solve it for 0 to 12 interval. Initial values are 0, 1, 1 at time t equal to 0. Okay, now we have to find what is the y value at t equal to 5 and 10 also. Okay, so just I'll give you a few minutes and then let me know the answers. Any answers for this? So you need to have time interval 0, 5, 10, 12. Okay, keep that in mind. Now going to the MATLAB code. What you do is your t-span, you give it as 0, 5, 10, 12 because we want specifically what's the time, what are the values at 5, 10, and 12. Initial value is 0, 1, 1. This is the ODE 45 equation. The function is EF. So basically, I'll show you the function. It will take t and y. And remember, if you have multiple equations, it should look as a column vector. So your first column will be this. If you have to extract y values. Earlier, you explicitly extracted y values. That is, s is equal to y1, p is equal to y3. Like that, you explicitly extracted. If you don't want to do it, you can directly write it like this, y2 multiplied by y3, and an expression like this. But I don't recommend you to write like this because you tend to make mistakes when you write it like this. So dy by dt, it's the first row, second row, and the third row. Okay. And then that will be the f function. And t span, you have 0, 5, 10, 12. Initial conditions is 0, 1, 1. And you just run this, and ts and ys is your output. You plot ts versus ys in a line plot, and the line width is 1.5. So let me just clear all this and running this. So this is how the plots looks like. The first y1 is blue in color, red is y2, and the yellow one is y3. Why is it like this? Because you have given sharp points. The time interval you have given, specifically you have given it. So that only has 0, 5, 10, and 12. So you have corresponding to 0, then 5, then 10, and 12. So that is why it is sharp curve. If you're just given directly 0 to 12, MATLAB itself will give you a very, very small time interval. So then you will be getting a very, very smooth curve. Okay. Now these are the values. Okay. So the first one is this is corresponding to time t equal to 1 for y1, y2, and y3. So the first column is for y1, second column is for y2, and the third column is for y3. And row means it is for 0. First is 0, then 5, time equal to 5, time equal to 10, and time equal to 12. So just like we did earlier, if you want specifically want to know what the y1, y2, y3 value is, since you know the ys, you can directly go to the index of the ys, okay, and extract it from there. You have to just know how the ys will look like. You need to understand each row corresponds to each time and each column corresponds to each variable. Okay, if you know that, you'll be able to extract it from the ys. I hope that is clear. Now moving on to the next question. This is a second order equation. This might be a bit tricky, but just think for a while and then we'll try. I'll show you the answer for this question. The trick here, what we have to do is, since we know, okay, what we do is we have to, this is a second order ODE, which means you have your d square by dt square term. So first, what you have to do is, this you have to first convert into two set of ODEs. How do you do that? Two set of first order ODEs. How do you do that? You write dx by dt is equal to y. Okay, so that becomes your first equation. Dx by dt is equal to y. Now you again differentiate. What will happen? D square x by dt square is equal to dy by dt. That's what you get. Now you substitute dy by dt here. Okay, and dx by dt is what? That is y, right? And x and omega t, everything remains the same. So now you get two equations. First equation is dx by dt is equal to y. Second equation is this becomes dy by dt. Dy by dt is equal to this whole part you can take to the other side. So now we have converted this into two first order ODEs. Your first variable is x, your second variable is y, and both are dependent on your t. T is your denominator. So now you know how to solve two set of, know how to solve two ODEs together, right? Omega is given to you. Initial condition is, for x, the initial condition is 5. So dx by dt, when you write that equation, the initial condition is 5. But the next equation, okay, dx by y, you write another equation, right? dy by dt. Okay, so y's initial condition is 0. So you write an ODE equation accordingly for time t equal to 2 and t equal to 5. So let's show that. This might be a bit tricky, but if you have doubts, you can just ask me in the next session also. That is completely fine. So your initial condition is 5, comma 0. What you need is your t-span is 0 to 5 because I want to know what the behavior is at time equal to 2 and time equal to 5. So 0 to 5 and your ODE solver takes the variable sin fun. T-span is 0 to 5. Your initial condition is 5, comma 0. Now let's see what a sin fun does. Okay. In sin fun, it takes two variables. Your first variable is x. Your second variable is v. Basically, I'm writing here dx by dt is equal to v. Okay, not y. Dx by dt is equal to v. So your first equation is dx by dt. So basically, take here dx by dt is equal to v. Basically, my first equation. Next equation will be dv by dt. So that is this one. dv by dt will be equal to basically the equation that I had in the question. That is minus of sine omega t 3v. Why v? Here in this equation it is written dx by dt. And I've always and already I've declared that dx by dt is equal to v. So here v comes plus 2x. So this will be a first equation. Dx by dt equal to v. Next equation will be dv by dt. That is d square x by dt square is equal to this equation. I have two equations like this. I give it as a column vector. That will be given as an input here. Now I'll just clear CLC. I'll run this. You will get the YSOL. So basically YSOL is like this. Here each row corresponds to time. So this is corresponding to t equal to 0, first row. This is corresponding to t equal to 2. And this is corresponding to t equal to 5. First row corresponds to x values. Second row, sorry, first row is dx by dt, right? So the first column corresponds to x values. Second equation was dv by dt. So the second column corresponds to the dx by dt, the v dx by dt. So here at x is equal to 2, our x value is first column, second row. At t equal to 5, x value is first column, third row. Okay, you get the x values here. Is this clear? Any doubts? I hope this is clear. Now I'll go on to the next question. I'll give you a few minutes and then we'll discuss answers. So here we have a reaction, A going to B and B going to C. And we have three equations. dA by dt is given by minus k by A. dB by dt is given by this equation and dC by dt is given by this equation. We have all the initial condition. At t equal to 0, we have a0 and b and a0, you can take it as 1. Okay. b0 and c0 is nothing but 0, 0. K1 constant value is given, K2 constant value is given. We have to find what is your A, B, and C value. Using ODE 15s with respect to time, you have to basically plot the concentration. So you know how to write equations when we have multiple ODEs. So let me just clear this. PLC. So when you have multiple ODEs, I am writing my time span I'm taking from 0 to 20 seconds. My initial value of A0, I'm taking it as 1, B0 is 0, C0 is 0. Okay. Now the ODE 15 as I have a function called rates. Let me just take rates. Rates take T and Y. Okay. And the first Y1 means it corresponds to A. Y2 means corresponds to B and Y3 corresponds to C. The order has to be very specific. So this is your first equation. This is 0.1 A. Is this right? Let us just check. Yes. The equation is K is equal to 0.1. So it is minus 0.1 A. Second equation should be 0.1 A minus 0.5 B. So let's check if it is right. So it's 0.1 A minus 0.5 B and this is 0.5 B. So this was the equations that we have. You have to give it as a column vector. So this is your first row, semicolon, second row, semicolon, third row. Okay, so this is the output d by dt. Now going to problem back. Now we have the t span from 0 to 20. Their initial values is 1, 0, 0. Give us as a vector. Now you have to plot t. Basically, when you do this, you will have three columns. The first column corresponds to your A values. Second column corresponds to your B values. And the third column corresponds to your C values. And you will have to plot this. I'll just run this and show to you. This is how the curve looks. I'll just show you the t values. It goes from 0 to 20. And your y values, there will be three columns. This corresponds to the initial value of A, initial value of B, initial value of C. And this is how A, B, and C changes. Like when you go down the column, you'll understand how the A value, B value, and C value changes. Okay. Now we'll have to plot it accordingly. So for plotting, what you do, you plot the T versus the first column. For all rows, first column will be your A. I'm plotting it as a circled lines. Again, T versus B values, that is a second column. And T versus third column, that is a C values. Okay, with circled lines. I plot it together, I get a plot like this. So this you have, in chemical engineering, you would have observed when you have a reaction A giving B and B giving C. What happens? A's concentration exponentially decreases. C's concentration, C is which is a final product, that also increases. But B, what will happen? B's concentration first it will increase and then it will decrease. Why? Because B starts to form from A, but B is getting converted to C, right? So because of that, B's concentration will first increase, it will reach a maximum and then it will decrease. Okay, I hope it is clear. Any doubts? The problem also, just let me know. Now going to the last question. So this is the last question. We have two equations, dy by dt and dx by dt. Okay, so y is the concentration of cell mass and x is the concentration of penicillin. So now we have to find the concentration of cell mass. That is, you need to find y at t equal to 1. Y0 conditions that's been given to you and your t span will be from 0 to 1. I'll give you 1 minute and then we'll discuss the answer. Shall we discuss the answer? So you have the initial condition 0.03 and 0. and time span should be from 0, comma 1. So your initial value is 0.03 and 0. Your T span is from 0, comma 1. You call ODE 15 years, same syntax as ODE 45. And this is your function, firm and fun. Okay. Now T span is given, Y0 is given. We'll see what this firm and fun does. So firm and fun takes T and Y values. Out of this Y, the first value will be the cell mass and the second value will be the penicillin mass. So X, Y, and X is taken. And this is your first equation. You have to put semicolon and then you have to put the second equation, right? So you get d by dt. You get two ODEs simultaneously. Now you give this as an output. Now I'll just run this for you. And you will get your TS and YS as your solution. So corresponding to TS, TS goes from 0 to 1. And correspondingly YS also, the first value will be, first column will be cell mass, second column will be the penicillin. Okay, what decide is we need to get the cell mass at the t equal to 1. That is the last value. So how do you extract that? You can write display and you will extract ys, that is solution vector, end, which means the last row, the first column, that will be the cell mass. And that value is 0.93965. You can just confirm it here. 0.93965. Is this clear? How to use ODE solvers, and you can solve any kind of problems using this. And I hope that the reservoir problem basics also you would have understood by now. Any doubts? Okay, if no doubts, you can leave the session. I'll inform you about next Friday's lecture. It might be postponed to Saturday. I'll just inform you beforehand. Okay, you'll get a message, like you'll get an email notification, and it'll be there in the announcements page also in the course web page. So thank you so much for attending the session, and please join for the next session also. You may leave. I will be closing this meeting.